Next, we're going to quickly overview trigonometric functions. We will not go through very much in details, but rather build an impression how they look like. So we will start with most popular functions, which are sine and cosine. First of all, I want to show you quickly the basic function. So for example, if f of x, our function is sine x. So the graph, let's say this is y and this is x. We can also write it as y equals to sine x. So a function of sine x for the basic function will go from 1, and here we have minus 1, and its periodic function, so it goes like this and this. This we call a cycle, and here is 2 pi. So it's periodic function, so we can continue to draw it further, and here will be 4 pi and so on. If we look at cosine x, it will look like following. Cosine x is also a periodic function with period equal to 2 pi, but it looks a little bit different. So it starts from here and goes like this. So this is a cycle of cosine, and it's also equals to 2 pi. So we can also continue this function further. If we put these two graphs together in one graph, you can see here that sine and cosine have the same shapes, and both graphs are shifted copies of each other. And if you can see here, it's shifted by x equals to half pi radians. So here on this line, this is radians. And if you see closely, sine and cosine, they're shifted on this amount. Here, here, here. That's why the domain of both functions is the same and it's equal to real numbers. The values sine and cosine repeat each other according to the following rule. Sine here has a cycle. And after this cycle, it will repeat itself. And here we will have 4 pi. So, but this function here, this part of sine is equal to this part of sine. So that's why they call periodic functions. And whenever we add 2 pi to the radiant, we will get the same function again. Same goes with the cosine. It means that for any number of x, sine and cosine are both periodic with period is equaling to 2 pi. Since sine and cosine have the same shape graph, both graphs are shifted copies of each other, and they are shifted, as I told you before, for x equal to half pi radians. So then if we add half pi to sine, or if we subtract from half pi x, we will get cosine x. And same goes with the cosine. If we move it either here or half pi there, we will end up having sine x. If we look closely to the graph, again I will show sine will be here, and then we can continue it like that. Sine is symmetric about the origin and thus is odd function. And cosine, on the other hand, is symmetric about y-axis, and hence it's even function. And if you remember the rules that we had for odd and even functions, so that's why sine of minus x will equal to minus sine x, and cosine of minus x will just equal to cosine x. So in general, all the roots are also periodic. The roots for sine will be pi, 2 pi, 3 pi, and so on. And for example, for cosine, the roots will be half pi, 3 pi divided to 2, and so on. So the next function that I want to talk about today is tangent function. So the tangent function looks like this. We can find tangent if we divide sine by cosine. Since cosine is in denominator, very important here to mention that x cannot be equal to roots of cosine. In the set of notation, domain for the tangent function will be defined as following. We have all real numbers except u, where we define u as k pi plus half pi for all integers. Because here is a radiance where cosine x will equal to 0, and we don't want that. As you can see here, the tangent function is periodic and the period is equal to pi. And it's symmetric through the origin, just like sine, and it means that tangent is odd function. And because tangent is an odd function, tan of minus x will be equal to minus tan x. And important to mention that roots of sine function are also the roots for the tangent function. So this was a very quick review of important trigonometric functions. Now we came to the last part of our chapter, which is transformations of functions. So some of them already we saw before in specific examples when we overviewed monomials, power functions with coefficients, etc. So you already have an idea, but here we will talk about transformations more in general form that can relate to all functions. And first of all, we will look at scaling. So there are two types of scaling. First one, when we scale the function itself, or also it's called scaling function values. Depending on the coefficient value, this transformation will be called either vertical stretch or vertical compression. So first example is vertical stretch when we have coefficient a larger than 1. So here we have an example of basic function sine x. And we had a coefficient which is larger than 1, which is equal to 2, and made it as 2 sine of x. So what's the difference? This one is sinus x, and this one is 2 sinus x. So if you look closely, we had our function, the blue one, from 1 to minus 1. And here we have it from 2 to minus 2. To explain it a little bit better, let me just show two graphs separately. Sine x. The coefficients in front of sine is equal to 1. Thus, our function will go from minus 1 to 1. So it will go like this, and so on. And now, what happens if we have AF equal to 2 sine x? So now we have 2 here and minus 2 here. So now our graph will do so-called vertical stretch. So if some of you don't remember, this is vertical line and this is horizontal line. And that's why it's called vertical stretch. We stretch it vertically based on coefficient in front of the function. And what happens if a is smaller than 1 in the interval from 0 to 1? So it means that obviously it will be some fraction. It's called vertical compression. And in our example, the coefficient will equal to half. So instead of stretching like here, it will go in different direction and become more flat. This is half here and minus half here. So this is very logical. When performing such transformation, the domain of the function remains unchanged. The graph of non-constant functions becomes steeper when a is larger than 1 and flatter when it lies between 0 and 1. But what happens when we scale the argument of the function? So if we scale the function argument, which is a little bit different here, so you see before it was scaling the function itself or function values, and here we're scaling the argument. It means we're scaling something that lies inside the function here. The graphs also looks a bit different. The stretch and compression in this case will be not vertical but horizontal. And for example, for b from 1 to 0, it will look like this. It will go to the horizontal stretch. Here we have cosine instead of sine. So here we have coefficient, which is smaller than 1 here in our example, and it stretches horizontally in this direction. And if b is larger than 1, then as here we have cosine x and cosine of 2x, it will go to horizontal compression. So you can see here it will compress horizontally. Also important to mention that domains of f of x and fx with coefficient b are often different. The next transformation is reflection, which is also often called as mirroring. It means that after this transformation, the function will look like its own mirrored version. To perform this transformation, we should multiply function of its argument to -1. Again, depending on what exactly is changing function of argument, we get two different outcomes. So in first case, we get vertical reflection. And when we have a look at fx, becomes f of -x. So for example, I can also show here on two different graphs, sine x and minus sine x. So sine x will start here and look like this. So this is sinus x. Minus sinus x will act differently. It will go like this instead. Minus sinus x, it will be mirrored reflection of sinus x. Both minus f and f have the same domain, just like when scaling with vertical direction. The graph of minus f is mirrored version of the graph minus f about x-axis, the vertical mirror image. If we multiply to -1 function argument, minus x here, it will look like this. So it's called horizontal reflection. So we can see here example was tan x and tan of minus x. And for the argument, it's called horizontal reflection, and it's mirroring about the y-axis. So basically, they either do vertical or horizontal reflection. And final transformation that we will cover today is shifting. If the function value or the variable have a constant added or subtracted to them, then the graph of the function gets vertically or horizontally shifted without changing its form. So shifting means that we add or subtract something from function value or from the variable of a function. So depending where exactly we're adding or subtracting, it also will differently reflect on the graph of the function. So first of all, if we add or subtract something to function itself, we have a vertical shift. So we move around the y-axis, either up or down. Here is an example of sine x and sine x plus 1. And if we add or subtract something from argument of the function, we move around x-axis. It's called horizontal shift. So here is an example of sine x and sine of x minus 1. So we were here and then we moved to 1 here. So that was it for today. And in today's chapter, we had a lot of material covered, different types of functions, how they look like, what kind of transformations you can do with them. And next time, if you see some kind of a function, you can picture it in your head, how it looks like. Thank you for coming to our course, and see you in the next video.